Distinct metamodels of smart cities have been developed in order to solve the problems of cities in relation to different socio-economic indicators. In order to guarantee human rights, information security plays an important role in contemporary society. From an infection by malware, malicious and software, a person or institution can suffer irrecoverable losses. As for a person, bank passwords, social networks, intimate photos or videos can be shared across the World Wide Web, which will affect finances, dignity, and mental health. On the other side, an institution may have its vital data inaccessible and/or information from its respective customers and employees stolen. In synthesis, the theft of intimate information can lead to cases of depression, suicide, and other mental disorders. Information security is essential to guarantee human rights in contemporary society. Increasingly, companies have been investing in digital security as new technologies in antivirus, firewall, and biometrics devices in order to avoid cyber attacks. Despite the efforts and investments, cyber attacks have been causing billions of damages and in increasing order. Despite being criticized for more than a decade, the antivirus's modus operandi is still based on signatures when searching for suspicious samples in a database named Blacklist. Through the VirusTotal platform, this proposed work explores 86 commercial antiviruses with their respective results presented in Table 1. We utilized 3,146 malware obtained from the ReWima dataset. The objective of the work is to verify the number of malicious samples cataloged by antiviruses. The motivation is that the acquisition of new malware is primordial to combat malicious activities. The larger the dataset, named the blacklist, the better it tends to be the defense given by the antivirus. First, the malware is sent to the server belonging to the VirusTotal platform. At this point, the malicious files were analyzed by VirusTotal's 86 commercial antiviruses. Then, the antiviruses give their diagnostics for the samples submitted to the server. VirusTotal allows 3 different types of diagnostics to be issued: benign, malware, and omission. For the first VirusTotal possibility, the antivirus detects the maliciousness of the suspicious file. Within the proposed experimental environment, all submitted samples are malware documented by incident responders. The antivirus hits when it recognizes the malignancy of the investigated file. Malware detection shows that the antivirus offers robust support against digital invasions. In the second possibility, the antivirus certifies the benignity of the defined file. Then, in the proposed study, when the antivirus claims the file is benign, it is a false negative, as all the samples sent are malicious. In other words, the investigated file is malware. However, the antivirus mistakenly attests to it being benign. Within the third possibility, the antivirus does not give an analysis of the suspect application. The omission shows that the investigated file was never evaluated by the antivirus, so cannot be evaluated in real time. The omission of diagnosis by antivirus points to its limitation on large-scale services. Table 1 shows the results of the 86 antivirus products evaluated. The McAfee GW Edition antivirus achieved the best performance by detecting 99.11% of the investigated malware. One of the largest adversities in combining malicious applications is the fact that antivirus manufacturers do not share their malware blacklists due to commercial disputes. Through the analysis in Table 1, the proposed work points to an aggravating factor of this advantage: the same antivirus manufacturer does not share their databases among their different antiviruses. Observe, for example, that McAfee GW Edition and McAfee antiviruses belong to the same company. Their blacklists, although robust, are not shared between themselves. Therefore, the commercial strategies of the same company disturb the confrontation against malware, which demonstrates that antiviral manufacturers are not necessarily concerned with avoiding cyber invasions but with optimizing their business incomes. Malware identification ranged from 0% to 99.11%, depending on the antivirus. Overall, the 86 antiviruses identified 54.84% of the examined malware, with a standard deviation of 39.67%. The elevated standard deviation shows that recognizing malicious files can change abruptly depending on the chosen antivirus. The protection against digital intrusions is in the function of choosing a vigorous antivirus with an expansive and upgraded blacklist. Overall, antiviruses certified false negatives in 14.34% of the cases, with a standard deviation of 21.67%. Attention to the benignity of malware can be implicated in unrecoverable damages. A person or institution, for instance, may begin to trust a certain malicious application when, in fact, it is malware. Nevertheless, as an unfavorable aspect, approximately 17% of antiviruses did not express an opinion on any of the 3,136 malicious samples. On average, the antiviruses were omitted in 30.82% of the cases, with a standard deviation of 40.97%. The omission of the diagnosis focuses on the constraint of antivirus in recognizing malware in real time. Due to difficulty in combating malicious applications, commercial antiviruses do not have a pattern in the classification of malware, as found in Table 2. We have chosen 3 of the 3,136 malware to exemplify the miscellaneous classifications given by commercial antiviral activities. As there is no pattern, the antiviruses use the names that they want. For example, a company can identify a malware as malware.1 and a second company can identify it as malware 12310. Therefore, the lack of a pattern disturbs the cybersecurity strategies since each category of malware must have different treatments, vaccines. It is concluded that it is impracticable for supervised machine learning to adopt pattern recognition for malware categories. Due to this confusing tangle of multi-class classification provided by specialists, antiviruses, as seen in Table 2, it is statistically improbable that any machine learning technique will acquire generalization capability. The state-of-the-art antivirus recommends extracting features of the suspect file, preventively, before executing it. Our dataset contains 6,272 executables, 3,136 malware samples, and 3,136 other benign samples. Hence, our dataset is suitable for learning with neural networks because the number of samples of the two classes is the same. Malware in the authorial dataset are broadly used in various malicious activities. They can be worm, virus, hack tool, Trojan horse, backdoor, constructor, hoax, exploit, rootkit, spyware, botnets among others. The executable file is submitted to the disassembly process through reverse engineering. For example, reverse engineering consists of taking apart a machine to find out how it works. In total, there are extraction of 630 features of each executable. Compared with other classifiers, the main feature of ELM, Extreme Learning Machine, neural network is the speed of training. The goal is to cluster the executables into two classes, benign and malware. The constraints of digital surveillance mechanisms can be overcome by artificial intelligence technology based on neural networks. Artificial intelligence is able to automate many jobs, analyzing thousands of data, extracting features, and classifying them. The artificial intelligence can recognize in real time the statistical patterns of the behaviors previously classified as suspects. Despite their extremely high accuracy, the latest neural networks engines, especially the deep nets, may take several days to complete the training phase even on a supercomputer. As an aggravating factor, deep networks have lower parallel capabilities because these layers are sequential. To prove our theoretical background, the authorial antivirus employs shallow morphological neural networks instead of deep convolutional networks. Our antivirus enables high performance, large capacity of parallelism, and simple, low-power architecture with low power consumption. We concluded that our solution assists the main requirements for the proper operation and confection of an antivirus in hardware. The learning of ELM's networks is based on kernels. The kernels are mathematical functions used as learning method of ELM's neural networks. Kernel-based learning offers the possibility of creating a nonlinear mapping of data without the need to increase the number of adjustable parameters such as the learning rate commonly used in neural networks based on backpropagation. In ELM neural networks, a linear kernel, for illustration, is able to solve a linearly separable problem, according to the same thinking. Sigmoid, radbus, radial basis function, and sine kernels are able to solve problems separable by sigmoid, radial basis and sine functions. As a counterexample, consider a linear kernel applied to sigmoid and sine distributions. Visually, it can be observed that the linear kernel does not correctly map the boundary decision of the sigmoid and sine distributions. In other side, the successful of our MELM kernel involves their ability to model any boundary decision, because their mapping does not obey conventional geometric regions such as ellipses or hyperbolas. Our MELM can use mathematical morphology to normally identify and model n-dimensional regions related to different classes, which can naturally detect the body shape present in the image. Visually, it can be observed that our MELMs can map different distributions in a satisfactory manner, involving different applications. In application level, our authorial antivirus achieves the average maximum performance of 99.76% with a standard deviation of 0.17% through the MELM kernel dilation with 500 neurons in its hidden layer as seen in Table 1. Therefore, our MELM dilation kernel presents the excellent quality of not suffering abrupt changes due to the initial conditions. It would be emphasized that the authorial dilation kernel obtained the best average accuracy regardless of its architecture. We claim that our morphological kernels are able to adapt to any decision boundary. Because they are inspired by mathematical morphology, our MELMs are able to model any mapping present in the decision frontiers of neural networks. Our objective is to create a computationally high-performance antivirus with large parallelism capacity even when running on slow devices, hardware with low processing and storage capacity. Our authoring coprocessor is compared to application-level antivirus replica. In order to avoid compatibility issues, the replication of the software-level antivirus replication occurs on the same platform where the coprocessor was prototyped. The application-level antivirus replica runs on the NIOS-2 processor. Preliminary results indicate that our antivirus is faster than a blink of an eye due to the multi-processing of data. It is emphasized that the human requires about 0.3 seconds in order to blink. In addition, there is no way for the user to disable/bypass the work of our coprocessor-based antivirus, unlike application-level antivirus. Being developed in a hardware architecture-level abstraction layer, our coprocessor-based antivirus is insensitive to social engineering attacks and/or operating system corruption. With the growth of social networks and more people connected via electronic devices, confidentiality of information plays an important legacy in maintaining the dignity, financial status, and mental health of genuine users. Then, our coprocessor antivirus hopes to collaborate in guaranteeing the human rights of contemporary society. Our expectation is to show how technology can be at the service of fundamental rights.